Is starting in on chapter 15. Seniors, this will likely be the last chapter you guys will deal with. It's a pretty big boy, so we'll just kind of play that by ear as the semester winds down on where you're at and where your end point is. But oh boy, that's embarrassing. I could tell you found it pretty well. So today we're going to be looking at section 15.1. So chapter 15 is about exponential, logistic, and logarithmic functions. And then we also have a little, or a big section of application here at the end. So these type of functions are related to a lot of financial mathematics. So we have some application talking about compound interest and annuities and appreciation, depreciation of goods, and that all happens kind of at the end of this chapter also. So it's a pretty big chapter. So we'll have spend a bit of time here. Today, what we're going to be talking about are specifically exponential and logistic functions. So I'll start with some definitions and some basic vocabulary. So an exponential function we're going to define as something that we can write in the form of a times b to the x. We call the a the coefficient. We call the b the base, and the x is the exponent. Now you'll notice that for that value for a, we say that a cannot equal 0. Why do we have that stipulation there? What happens if a is equal to 0? Great. So if a is 0, the whole thing just becomes 0, and that's a constant function, not exponential. If we look at the value for b, we have some restrictions on that. We say that b can't be 1 and it has to be positive. So what's going to happen if b is 1?
Whatever a is 1 to the n power is still 1.
Okay, 1 to the anything power is still 1, and then times a is a, and that's going to just be a constant function. We don't want that. Why can't b be negative? It's a little bit harder to see. Why are we disallowing b to be negative? Okay.
Because b has to be greater than 0.
Right, but why did we say that, though? Why don't we want negative values for b?
Oh, because...
What would happen if there were? Not necessarily. What if x was positive, or what if x was 2? Yeah, what about the exponent's going to be a problem? Okay, so here's nobody can in fourth hour came up with this either, and that's fine. I'd be pleasantly surprised. What would happen if the exponent, let's assume b was a negative number, and what if the exponent for the value for x was 1/2? What is that? What is the exponent of 1/2 the same as?
Oh, 1/2?
Yeah, an exponent of 1/2. It's the same as a square root. Can I square root a negative? No. What do I get if I try to square root a negative? Imaginary number. So this thing would have, if I allowed a negative for b, I would have infinitely many discontinuities on this, and that's just like an incredible nightmare. I don't want any part of that. That's not at all what we're trying to describe here. Everybody feel okay? So again, we have these restrictions on here. It's worth taking a minute, at least mentioning why they're there. So all exponential functions of the form y equals a times b to the x have a horizontal asymptote at y equals 0. But if we look at the four possibilities that I've color-coded here in orange, red, blue, and green, those are the four different possibilities of what a exponential function of the form a times b to the x could look like. You'll notice that each one of them has like a different end behavior, right? That only one end is following the horizontal asymptote, and the other end is bombing off to either positive or negative infinity. You guys can kind of see that. So again, all of them have the horizontal asymptote y equals 0, right? The x-axis. But if it's the blue one, the left end of the graph is following the horizontal asymptote going to 0, but the right end is bombing off to positive infinity. The green one, the right end is following the horizontal asymptote, but the left end is bombing off to positive infinity, and so on and so forth here. Okay? So the takeaway, what you want to remember, is that for all exponential functions, one end of the graph is following the horizontal asymptote, basically going to 0, and the other end is shooting off to either positive or negative infinity and growing basically as fast as anything in mathematics can grow. Real fast. It's okay? So let's look at our, just like a specific exponential function, talk about like, review maybe our exponent rules and like how we evaluate one of these things by hand. Now, obviously we can type stuff into the calculator and get the number to come out, but I'm not interested in doing that right this second. But before I do any of that, I want to first ask you guys a really important question. True or false? -2 times 4 to the x is equal to -8 to the x.
It's true. Wait. Oh, you can't have a negative exponent.
You can have an exponent on a negative number, that's fine.
You can't combine them because they're not to the
Wait,
same.
why is it a degree?
Yeah, so it is false. And Kendall says you're right, because the rules for exponents says that to multiply two exponents together, they either have to have the same exponent, and you can multiply the bases, or if you have the same base, you can add the exponent. But if you have both different base and different exponent, ain't nothing you can do. So the exponent on 2 is to the first, the exponent on 4 is to the x, 2 and 4 are different, 1 and x are different, nothing you're doing here. Everybody was okay with that idea? So again, that's a very common mistake I see students make. I always like to lead off, like how are we going to work with these exponential functions, with making sure that we're clear on this common mistake and explain why you can't do that in this situation. Okay. Next, what I want to do is just burn through a bunch of specific examples. So we're just going to compute like f of 2 and f of 0 and so on and so forth. So when we write like f of 2, what does that mean? Yeah, we're just plugging 2 in for x, right? So there we go. That's what we get. If I want to simplify this down, what do I do first? The exponent comes first, yep. Remember the order of operations. So 4 squared is 16. And then -2 times 16 is -32. There's our answer. Any questions there? Okay. If I do f of 0, again, we're just plugging 0 in for x. What do I get here? So anything to the 0 power is 1. is almost correct. There's one exception. 0 to the 0 is undefined. But any non-zero number to the 0 power is 1. Okay? So again, that's a rule of exponents that you guys would have seen in Algebra 2. Those sorts of rules for exponents, it's at least, I would say, the second time you've seen them. You probably did in Algebra 1 as well. It's kind of at this stage expected to be a mastery level skill. I don't mind going back and reminding you, but after a reminder, you guys should feel like, okay, either I review this for a little bit and make sure I got it, or like, oh yeah, I remember doing that, is kind of the expectation here. Ready to continue? Oh, good. All right, so if we do f of -3, we have that, right? How do I do a negative exponent?
Go into like a fraction.
Yeah, it makes a reciprocal. And 4 to the third is 1 over 64, or 4 to the third is 64, so we have 1 over 64. So that's -1 over 32. Again, the rule for exponents we're using is this guy. Okay, next one is f of 1/2. What does an exponent of 1/2 mean? It's a square root. And the square root of 4 we have to do first. So our rule for fractional exponents is that, right? The numerator is the exponent and the denominator is the index of the radical. You guys remember that rule? Again, these are all things that, like, okay, if you forgot it, but like once I show it to you, you're like, oh yeah, I remember that. Should be where we're at. Okay, our last one is a doozy. God bless you. Okay. So, as an aside, there's a lot going on here, right? So I remember that an exponent of an exponent, this is the same as the multiplication in the exponent. So with that in mind, I'm going to think about -3/2 as -1 times 3 times 1/2. Everybody's okay there? And then I'm going to want to think about like the order that I want to do that in. And I probably want to do 1/2 first, the 3 second, and the -1 last. Oh dear, got us again. So this is what I'm thinking about in my head. Why did I put the 1/2 as the very most inside thing? Is the square root of 4 easy? Yeah, right? Like I knew that right away. Let's knock that square root out first things first. Like I don't want that hanging around. Now, why did I put 2 to the third next? Or put the 3 next? Well, because like a whole number to a power is really easy to do. 2 to the third, piece of cake. That is 8.
And you got 1.
And then with the -1 exponent, that just makes a reciprocal. And I reduce and I'm done. So again, not attacking that as -3/2 is probably the way you'd want to think about it. So if the square root is easy to do or the radical piece is easy to do, I want to do that first. If it's not, I'm going to leave it probably till the end. But I either want to probably do that first or last. Everybody cool? And usually I'd like to divert the fractions as long as I can. So here below, I've gone back and recapped our exponent properties from Algebra 2 here if you didn't remember them. So we listed a lot of them off to the side there, but here's all of them that you would have run into there in your Algebra 2 course that we would still want to remember for this chapter. Anything look unfamiliar? Pretty standard fare, right? Okay. So we've talked about how to go from like an exponential equation or exponential function to points, right? That's what we just did, right? We had the input and we found the output. What I want to do next is go from points back to an equation. So we're going kind of in the reverse direction, right? So there's 2 situations that we'll need to deal with. The first one is the easiest one, and the second one's a little bit more complicated, although we can make it quite a bit easier with the use of technology, and we'll show you how to do that here momentarily. The first situation, what I'm looking for is one of the x values being 0. If one of the points that I'm given has the x coordinate 0, makes my life way easier. So I'm trying to write an exponential equation. If I have the point 0, 3 and I plug that in, I have that, right? What's b to the 0? 1. Except if b is equal to 0, right? Could b equal 0 here?
Yeah.
Well, let's go back. We're writing an exponential function, right? What are the rules for b? Can it be 0? No. So we are in the clear, folks. What great news, right? So that just tells me that a is 3. So I have then y equals 3 times b to the x. To find b, I'm just going to pick one other point, say this one. Does it matter which one I pick? As long as it's not the same one I just used, it doesn't. But like, come on, folks, pick the one where the x value is 1, so you don't have to do a radical if you have the choice. So I divide both sides by 3, and I get b is 5. If I take both of these together, then I got that. Pretty easy, right? Should I write that as y equals 15 to the x? No! Why not? The bases are different, 3 and 5, and the exponents are different, 1 and x. Can't combine them. Everybody feel okay? The second situation we'll look at is where none of the x's are 0. So to do this, what we're going to do is we're going to create a system of two equations. So we're going to take the point -348 and plug it into our exponential equation, and then take the point -112 and plug that into our exponential equation. That gives us two separate equations, each with two variables. That's a system of two equations. Last year in your Algebra 2 class, you would have spent some time solving systems of two equations. My suspicion is in that class, you only dealt with the equations where the variables were being added or subtracted from one another rather than multiplied. So let's just kind of talk through what we're going to have to do differently in this situation. So when we had variables that were added and subtracted, and we and we wanted to use elimination, we added or subtracted the equations together to cancel variables, right? If our variables are multiplied together or divided to, what are we going to use to do our elimination? Multiplication and division, right? Yeah, exactly, the opposite. So I'm going to refer to this first equation as equation A and this one as equation B, just so I can like notate what I'm doing on the sheet of paper so you guys, if you look back at it, you understand what we're doing. So what we're going to do is we're going to divide the two equations together. Now, usually what I want to do is I want to pick the numerator of my division problem to be the equation with the bigger value for the exponent. So that would be equation B, because -1 is bigger than -3. So I'm going to do equation B divided by equation A. So if I look at their left-hand sides, that would be 12 divided by 48. And if I look at their right-hand sides, that would be A times B to the -1 divided by A times B to the -3. Everybody cool with what I did? What do you notice I can do? I can reduce the A's, yep. And I can reduce the 12 over 48, that's just 1/4. How do I reduce B to the -1 over B to the -3? They have the same base, so if I'm dividing them, I can subtract the exponents. Yup. So what's -1 minus a -3? 2. So how am I going to cancel out that 2 in the exponent? Square root. Now when we square root both sides of an equation, what do we have to remember? When I square root both sides of an equation, what do I have to remember? What? Somebody started saying it. Plus or minus. That's what I was looking for. But do I really need a plus or minus in this situation? Which one do I not need? Why can't I have the minus? Because B always has to be positive, right? So what is the square root of 1/4? How do you square root a fraction? You square root the top. The square root of 1 is 1. And you square root the bottom. The square root of 4 is 2. Everybody's okay? Now that I've found B, I can plug that back into either equation A or B. I'm going to plug it into equation A because the exponent is closer to 0, which makes life usually a little bit easier. What is 1/2 to the negative 1? 2 to the first, right? I'm just making a reciprocal. And if I divide both sides by 2, then I get 6. And I put those two boys together. And there we go. You guys happy? Now, this process was quite a bit more complicated than the previous one, right? Good news for you. Calculator can do this. Would you like to see how?
Yes.
Yeah, I thought maybe you would. So if you have your graphing calculator with you and you'd like to follow along, I invite you to take that out now to do so. If you prefer to sit and watch, that's fine. I also have extra calculators on my desk if you're like, oh man, I forgot my calculator, but I really want to follow along. They're there for you to use. All right. So the first thing I'm going to do is want to enter my 2 points into my calculator. So to do that, I'm going to press the Stat button. And from the Edit tab, I'm going to select the Edit command and type in my 2 points. So I had -1 and 12, I think. And the other, oops, oh boy, that's not the right spot. And the other was -3 and 48. I think I remembered those correctly. Am I right? None of you guys have it written down. I'll look. Yes, good. I'm just stalling here in case anybody's still typing. What I'm going to do now is I want the calculator to write an exponential equation from these 2 points, right? Hey, didn't we do something like this way back in like chapter 11 when we wrote all those regression equations? Yeah, that's exactly what we're doing. So to get that, what I'm going to do is I'm going to exit back out to the main screen. And I'm going to press the Stat button again. But this time I'm going to go over to the Calc tab. And I'm going to scroll down until I see the command expreg. And I'll select that. And I'll hit Calculate. And look at what it spit out for me. It says, here's your equation, a times b to the x, where a is 6 and b is 0.5. Isn't that the exact same thing we just wrote? Isn't this the exact same process we used in chapter 11? Isn't it nice where we can go and recycle the process from a previous chapter into a new chapter, where it's just like, hey, remember this? Doing the same thing.
Why does it have the R2 or the R?
Doesn't need them. We don't need them for this because when we do this, we're just using 2 points. It'll be a perfect fit, so they don't matter.
Okay.
We don't need them. If we're in chapter 11 still, I would describe to you how to get them to show up, but since we're not there, I'm not worried about it.
Okay.
Cool? Okay. Everybody happy?
Yeah.
All right. Let's continue on then. So, you guys know in geometry, we have this number that we call pi, right? What is pi approximately? 3.14. What kind of number is pi? It's irrational, right? What does irrational mean? It goes on forever and the decimals repeat with no pattern, right? There's no pattern in the decimal. You know, like 1/3 is 0.33333, and there's a pattern. It just threes all the way out, right? There's no pattern to pi. Well, there's another irrational number that's really important to us that we're going to give the name E. E is approximately 2.72. Okay, we're going to refer to E as the natural base, or we could call it Euler's number. That's named after Leonard Euler. He's on the wall back there. One of the most productive mathematicians in history.
So since pi is circle, what is this number from?
We'll get to kind of where this number tumbles out from. It has to do with like continuous growth. But we'll talk about that a little bit later when we talk about compound interest. It fits really nicely, and you can see, or you can appreciate like where it comes tumbling out. And we'll get to that, but it's a little bit of a sidetrack to do it now. It fits more naturally a little bit later. But we define E as the limit as x goes to infinity of 1 plus 1 over x to the x. And when we do that, that's where that number comes piling out of. We'll talk about the significance of doing that and why somebody did that and why this number is really important and representative, but we're going to get to that later. So one of the important things for or uses for E application is ideally exponential functions can kind of have any number as a base, right? And if I want to compare two exponential functions with different bases, that's really difficult to kind of compare just by looking at the equation. So we'd like to be able to standardize that process. The way we choose to standardize it is we choose to rewrite all of our exponential functions so that they have base E. That's a way to, then I can make a meaningful comparison between my exponential functions because now they have the same base and it's easier to make a comparison. So we can define an alternate way to write an exponential function as y equals a times k to the x. And I guess we should say the same thing about a, is that a is not 0 and k is not 0. Because otherwise everything is just trivial. Everybody's okay?
Yeah.
All right. So now that we have these two different ways of writing exponential functions, what we want to do is classify the types of exponential functions we have into two categories. Those two categories are growth or decay. So we say something's in exponential growth if it's increasing as we go from left to right. So if I look at this guy, he's increasing. Or if we look at this guy, we're increasing. And we call it exponential decay if it's decreasing as we go from left to right, which are what these two guys are. Everybody feel okay there? Now, it's really easy to tell growth versus decay by looking at the picture, but what we'd like to be able to do is be able to tell growth or decay by looking at just the equation. So I've labeled these guys 1, 2, 3, 4, these pictures, and we're going to talk about which picture is represented when A or B are specific values or A and K are specific values. Okay? So if I look at graph 1, I get that if we're doing y equals a times b to the x, and a is positive and b is greater than 1. And I get graph 2, the other type of growth, when a is negative and b is between 0 and 1. So like a half or a third or 0.75 or something, you know. And I get decays. This one, graph 3, when a is positive and b is between 0 and 1. And I get this decay when a is negative and b is greater than 1. And I can make a similar statement here about if I've written, or a similar statement if I've written my exponential function as y equals a times k to the x. So graph 1 comes from when a is positive and k is positive. Graph 2 from when a is negative and k is negative. Graph 3 and 4 when the signs are opposite. One of them's positive, the other's negative. So, as an example, if I ask you whether the function is positive or negative, you should be able to just look at the values for a and b, or a and k respectively, and be able to pick out which situation we're in. So we got the first one, the a is negative, and the b is greater than 1. That is this situation. So we know we're doing decay. Is everybody okay there? If I look at the next situation, here we have a is -5, that's negative, and k is -2, that's negative. So this is situation 2. So here we have growth. Is everybody cool with how to identify if something's growth or decay by looking at the equation? You basically just check it against the criteria we listed, and all there is to it, right? Let's look at this example. So this problem says, given that the population of a certain city in 1990 is 782,248 people, and the population of the same city in the year 2000 is 895,193 people, and assuming the population growth is exponential, in what year will the population reach 1 million people? So when you read this question, you should read this as a two-part question. So the first part here that I've highlighted in yellow, you should think about this as 2 points. That we want to write an exponential function for. Everybody's okay there? You hear that in the words and like, okay, I see that. I see 2 points. Date and pop, another date, another pop. That's like an X and a Y. That makes sense, right? What's going to be the best way to write that equation? It's the easiest way to do it. Use the calculator. That's what I'm going to do. So if you have your graphing calculator out and you'd like to follow along, I encourage you to do so. So stat, edit. We got 1990, and then 2000. And then grab the number here. 782, 248. And then 895, 193. Everybody's okay here? Okay. Before I do this, I want to point out something before I finish anyways. I want to point out the second half of the question says, in what year will the population reach 1 million people? I'm going to call this actually f of x instead of y. So here, what we want to do is we want to solve f of x equal to 1 million. So the way I'm going to do this is I'm going to do that piece on my calculator also. I'm going to do it graphically. So when I generate my function in the yellow section, I'm going to want to store that into y1 or one of my y equals slots so I can solve this graphically in a minute. I needed to mention what the second step of this problem is going to be to justify why all of a sudden I want to store this equation when we didn't bother with it before. Okay. All right, back to this. I got my points. Exit out of there. Then we do stat, calc, exp_reg. That's at number 0. I got my stuff in L1 and L2, but I'm going to store this now into Y1. Who remembers where the Y's live? Good. Vars over to Y vars. Pick function, pick Y1, and then press enter. Everybody's okay? So if I was going to write my answer down, let's say I want like 5 significant figures. So what would I write for A here? No. I'd start with 0.00000. Yeah, because it's to the -6. I have 5 zeros out front, and then 17277. And then my B is 101,357. I think a 1.101. Go ahead, Max. Oh, nope, I was right. Okay. So again, like the directions will tell you how much to round on something like that. But ideally, when you're doing this in your calculator, you don't want to do any rounding. You want to carry all the decimals in your calculator because exponential functions, especially their base, are really affected by rounding too much or too little. Everybody's okay? All right. So by choosing the store option, it gives me basically all the decimals I need there to do a good job. And then I'm going to enter in 1 million into Y2. And now I want to sort out my window, right? Because I want to make sure I get a good picture of this. What is the smallest x value I'm going to be concerned with? Nope. Yeah, which was 1990. So that's what I'm going to choose as my x min. Now, I don't know how long it's going to take to get to 1 million, but going from 1990 to year 2000, I gained about 100,000 people. I'd guess to go from 2000 to 2010, I'd gain about another 100,000 people, which would put me just short of 1 million. So I'm going to say I'm going to say 2020. Give myself a little bit of slack there, but I'm just kind of making a guess. Is everybody okay with the guess that we made here, though? Seems appropriate. Now, what is the smallest y value that I'm concerned with? Well, if I look at my points, what's the smallest point? 782,248. Now, I'm not so crazy. I'm going to type in all those decimal or all those different numbers. I'm just going to go 700,000 seems close enough for me. Oops. That's one too many zeros. That's 7 million. And then what y value do I definitely need to be bigger than, or at least as big as? The 1 million, right? So I don't know, let's do like 1.5 million or something. Everybody's okay with how I chose my window? Typically, this is the hardest part for students, is using a little bit of common sense to choose a decent window. If I hit graph now, you'll notice that I have a nice picture. I can see the blue curve. That's my population model. And then the red line is the 1 million. To find that intersection, I'm going to press second in the trace button. I'm going to choose the intersect command. And because I have just 2 curves and 1 intersection, I just can press enter 3 times. And there it goes. It says in 2008.2. So I would answer then during the year 2008. Everybody's okay? If it said at the beginning of what year is the population at least 1 million? You'd say 2009. Very good. So you have to be careful with what the question is asking at the end. If it's asking the beginning of blah, 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 you have to round up no matter how close to 0 that decimal is. If it's, you got to round up. Okay? I think that happens in the homework at some point, so be careful on that. Everybody feel okay with what we did here, though? We'll show you guys eventually how to solve these things algebraically, but we're not there yet. We're just going to be using the calculator right now to solve these kinds of equations. The second, okay, so this is describing a population, right? Now, the graph of an exponential is going to look like this, right? Would we expect the population to keep increasing forever? Right? As x goes to infinity, would we expect the population to be infinite? No, what's going to eventually happen? You're going to run out of space or resources or whatever, right? Like eventually you run out of stuff to sustain your population. Everybody agree? So ideally we'd like a better function or a more suitable function to describe population growth. Maybe one that looks a little bit like this, where it starts off and it looks exponential, but when it gets up towards that carrying capacity, like where we start running out of resources, it levels off, right? This looks like a much better description of what population growth should look like. So there's a type of function that looks like this. This is called a logistic function. So our logistic function is defined as something of the form f of x equals c over 1 plus a times b to the x. Or I could write it as f of x equals 1 over 1 plus a times e to the negative kx. Everybody good there? Okay. A logistic function has 2 features. Well, it has its key features has 2 horizontal asymptotes. This is the only function that we'll talk about in this class that has 2 horizontal asymptotes. The 2 horizontal asymptotes are going to be at y equals 0 and then y equals c. Notice that the c is the, oops, that's a typo, is the numerator of the logistic function. That'll be like the upper bound or the limit to growth or the carrying capacity. You could use those terms all interchangeably. So as an example then, let's say we have the population of a city modeled by the logistic growth equation, yada, 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 where P is the population in the city T years after 1950. So that's an important piece, right? This tells us that, well, like we should say the year then is going to equal t plus 1950, right? Okay. At the beginning of what year, notice we have beginning there, so this tells us round up, no matter what. Will this, the beginning of what year will the city have 1 million people? So basically we just want to solve P of t equal to 1 million once again. Everybody cool? Okay. So I'm going to go to my calculator. We'll do this again on the calculator. So I'm going to type in my logistic function. It is much, much easier to do that if I have a horizontal fraction bar. So you do alpha and then the variable button, it'll give you the horizontal fraction bar. You see it on the calculator screen right there in green. So that I type that in, 1425,397 over 1 plus 21.783 times E. So look, second, and then the ln button down here gives me the E to the negative 0.04982, and then my variable. Everybody feel okay? All right. I'm going to go to my window here. So remember, t is the years after 1950. So my minimum value of t really should just be 0, right? That'll represent 1950. Now, I don't know how long it's going to take, right? Or even have a pretty good idea of how this is growing. So I'm just going to put like 150 in here. That'll take me all the way out to year 2100. If I have to extend that out further, it's fine. I can do that. I don't really know what to expect here. So I'm just going to pick a pretty long value or pretty, big chunk of the x-axis to look at. But that should probably catch it. The y minimum is always y equals 0 for a logistic. The y max is always the carrying capacity. That's the number in the numerator. I'm going to use 1.5 million instead of 100 or 1,425,397, like close enough, like that ought to do me. And then I'm hitting graph. So there's my logistic function. There's the line for 1 million, and that intersection is the value I'm looking for. So second trace, intersect command, because there's just two curves in one intersection, enter, enter, enter. So I get 79.002, we'll say. Now, I noted, because it's talking about the beginning of what year, I have to round up no matter what. So that's going to be 80. So my year should be then 1950 plus 80. So that would be the year 2030. How'd that feel here, dudes? It's all right? That's it for 15.1. So your assignment for that should be 1 through 16. Feel free to use the calculator. I encourage you to practice using the calculator to do these things. The solving exponential should be done using the calculator. That would be the expectation come the test for these sorts of problems where the numbers are really inconvenient. You should be quite well versed at using your calculator to write an exponential equation, then use that exponential equation to solve something, or exponential function to solve an exponential equation, I should say. But that's it for me. You guys feel good? Or at least not bad? Okay, I'm stopping here. Go ahead. Say hi to Max.
Don't come back.